spirit among countrymen. This year-long festival, designed on 1 month, 1 theme pattern, commemorates 75 years of progressive India and its glorious history and achievements under Azadi Ka Amrit Mahotsav. Today, we are entering into 9th month of its celebration, and theme for this month of May is future technologies. Talking about technologies, I must say technological evolution has been faster than human evolution. Where it took thousands of years for humans to evolve, it took only few hundreds for massive technological evolutionary shift. And we cannot ignore the fact that technologies are the sole magic that pulled the world through every unprecedented difficult times, ranging from green revolution to tech interventions, including vaccines for COVID pandemic. To discuss the future of technologies, today we have dignitaries with wide spectrum of expertise, and to open the event for their valuable insight, it's my honor to invite architect of this Pan-India initiative, Dr. Debapriya Datta, advisor Seed and State S&T Program, Department of Science and Technology, Government of India. It is under his leadership today that entire country is learning about advancements and achievements of India in S&T. Dr. Datta obtained his doctorate from Indian Agriculture Research Institution and joined Indian Council of Agriculture Research. Before joining DST-GOI in 1994, he gathered his expertise from nationwide prestigious institutions. Sir has also served as scientific counselor in the Embassy of India, Washington, D.C., where he has handled India and US Science and Technology Corporation at project and policy level. Thereafter, Dr. Datta has steered many more important policies and programs for providing STI vision to the nation. Sir, please.
Thank you, Alokika, and good morning to all of you, and especially.
Sir, we are unable to hear you.
Hello, can you hear me now? Hello.
Yes.
Yeah, because
yes.
I'm unmuted. Yeah. Can you hear me now? Yeah.
I can hear you, Alokika. You are unable to hear Dr. Datta. Let's confirm from the others. Are they? Harpreet, can you confirm? Can you hear him?
Hello. Yeah. Good
Yes,
morning.
I can unmute and I can hear all of you.
Great.
Okay. Thank you. Dr. Jatinder Kaur Arora for taking this VIGYAN UTSAV ahead. And we are in that cusp when now the Utsav has to be transformed into the action. And the actions, I think, which are the way of the evolutions of this State S&T Council network, an unique network of a center in the State Science and Technology collaborations, which started in the 1971, which is that in that way the more than 50 years of this network, in which different S&T councils, state S&T councils has formed in the different the time. But in this the progress, the Punjab has emerged as one of the the pioneer of the state S&T council, I will say the state S&T council movement, in order to take the science, technology, and innovation ecosystem of the state ahead, and has evolved and emerged as one of the national model. Now, within this model, now the future of the state S&T council networks, all of us are committed towards the catalysis or the catalyzing the state STI science, technology, and innovation ecosystem. So after this 9 months, now what we have come into that the main science, technology, and innovation ecosystem at a state level consists of mainly 6 of its component. At the core of this, it's definitely the research and development, then the the technology development, technology, the utilizations and deployment for the socio-economic the development of the states, the human and the organizational capacity building, including the infrastructure development, the policy, and the science, the S&T in the policy, and that the human resource development, that which are the main important 6 important components of the STI ecosystem. So in the context of this technology development, if you see that over this 9 months, we have discussed about the different aspects of this technology development. And this month, we are focused towards that the future of the the future of the technology. There is an, like the whenever you say the future technology, there is a very thin line between the futuristic technology and the the future technology. Since we are a part of the government, like we are focusing more on the future technologies, those technologies which will basically they strengthen the our government's main the focus of the Atmanirbhar Bharat. And in that is the reason that we are focusing on the future technologies which will make human life easier and the faster, the creating the new economic opportunities, creating a new job opportunities for the the human resources, and for the sustainable development and the practices all over. So in this the context, what we are looking that I'm very happy that today that there are some certain examples of that type of technology we are like going to see here in this the program. As we see here, like we welcome the the experts like Dr. Harpreet Singh will discuss about the cold spray as an alternate additive manufacturing process. Dr. Amandeep Singh Oberoi, like will talk about electrochemical hydrogen storage devices, which is important from the the energy independence of the country. And Dr. Vijay Kumar will discuss on the smart material designing for the future agriculture, which is the the core of development of the coming 25 years of the India's science, India's the growth story based on the science and technology, as has been the responsibility entrusted by our honorable Prime Minister to the scientific and the technological community. And also Dr. Arora, whether there is Mr. Patrick Herbert is here, the Consul General.
He's here. Yes,
Oh,
yes,
okay.
I can see. Yes.
So I from the the government of India, I welcome Mr. Patrick Herbert, and and I think this is the first time it shows that the technology has no boundary, and like when you at a state level, you really work with the international collaborations. With my little the experience of the international collaborations, but I understand that they when we look at it into the state SMT councils, the perspective for a technology or the knowledge and research and development, these international collaborations really strengthen that the science, technology, and innovation ecosystem again at the state level. So till now, today is the I think the 5th and 6th day of this month's discussions, where we have discussed, the different states have discussed about the status and their visions of the the future technologies which can give that the Atman or the self-sufficiency in terms of, like, as you know, that the globally, especially after the pandemic, and also the geopolitical situations has again emphasized a shift from globalizations to a more often the globally linked self-dependence, dependence. So I think this is the time to look into that at a state level, and how as a collectively at a national level we can strengthen that our vision and action towards an the technologies for the future, which will bring the the advantage to the majority of the people in the country. That means there is a link of the technology development should be in tune to the livelihood system of an 80% of the populations which live in like our rural areas, and so-called have to be brought into the mainstreaming of our socio-economic development. Also, there is a responsibility that the technology development per se, till now, it has developed more at at a global level, and we have brought it here. So there is an aspect of the technology development at a system level or a macro level. But if Atmanirbhar Bharat needs to be fructified, we have to think about that how towards the majority of the livelihood systems, efficiency to the livelihood system, we can develop the future technologies, the advantage of which can really improve the livelihood system efficiency of them. So, and Punjab being a state like which is a future, the future looking state, and which depends upon which has brought the the green the advantage of the green revolutions in the country. So the next level, the coming this 25 years, the livelihood centric, the technology, the future technology development. I hope that Punjab will take a lead and will will strengthen that this aspect of the STI ecosystem at not only at a state level but also at a national and the global level. So with this, the thought process that which we have organized this month's this VIGYAN UTSAV of focusing on the future technology. I again thank all of you, and I think just to inform you one thing, this my colleagues were saying, these 9 months on this virtual platform, we could reach out to the 3,300,000 people who have got they've linked with us, and at the end, today is Department of Science and Technology, Government of India's DST's annual day. DST is the completing the its existence of 51 years. We are celebrating the DST's the annual day today. So on behalf of DST, I wish you all the best and expect that in this today that the discussions what we'll do, it will give the direction towards that the future technology development, not only in the state of Punjab but to the national context. Thank you very much, and I really thank all the experts who have agreed to be here and take this VIGYAN UTSAV forward. Thank you, Dr. Jatinder Kaur Arora and all my colleagues from the State SCT Council Network.
Thank you, sir, for an informative talk, and congratulations on DST's Foundation Day. And we are grateful for you to consider Punjab as pioneer in state S&T Council movement. Moving ahead, I would like to invite Dr. Jatinder Kaur Arora, the Executive Director of Punjab State Council for Science and Technology. She is on multi-role journey, being the Chief Executive Officer of Punjab Research and Innovation Council, Member Secretary Punjab Biodiversity Board, Director Punjab State Biotech Corporation. She is recipient of several prestigious awards, to mention a few: Punjab Sarkar Praman Patra by State Government, National Award for Women's Great Development through Application of Science and Technology by Government of India, Great Woman Award in Science and Technology category by Indian Television Academy. It is result of her efforts that UNDP and Government of Punjab have conferred Council with SDG Action Award 2020 for Environment Sustainability. Not only this, recently, FICCI and IPSTE Academy has honored her with IP Recognition Award for PSCST's impeccable contribution in the field of intellectual property. Ma'am, please.
Can I have the presentation, Amandeep, the IT team? Dr. Datta, thank you for being here. And indeed, auspicious day today. We are celebrating DST's 51st year. I remember last year we celebrated 50th year, and with much fervor. You can see here the logo also of DST's 50th, which we have put across all our materials. And thank you, Mr. Patrick, for joining. In fact, Mr. Patrick Herbert took over as Consulate General very recently, a few months ago only, but the level of engagement and the level of energy he has brought in this region, I feel like saying he's a dear old friend. And thank you, Harpreet. I met Mudit last week we were together on a panel of FICCI, and the kind of grasp on the subject, how India as a country is going forward with the future technologies he had. It was a treat to listen to him, and I asked him if he could join today, and he's been kind enough to agree. I think Mudit will be joining shortly. We also have with us Amandeep and Vijay. As Dr. Datta mentioned, they would be sharing some cutting edge technologies which will make impacts in future. Let me take you through all. This is as we say, Vigyan Utsav, which means a festival. We carry this festive spirit along when this has been a beautiful journey. Every month we've been taking one topic, pan-India, and sharing this with our stakeholders, with everyone who takes interest in science and technology, make them take pride where India is, where we plan to be. And today also I can see the researchers, students, faculty have joined here as well as through YouTube and other social media. So I'm sure many of you who have been watching Rocket Boys would have seen the picture on the left-hand side, how in the resource deficient settings, India started its space program. And today, after having launched Mangalyaan, which was now, say, 7-8 years back, 2014, we did that. It had put India in the category of being Asia's first to reach at the Mars's orbit, and also first in the world to be the country which could do it in its first attempt itself. And as you know, we have a very strong space program in India, and I'm sure all of you who are fond of watching Robert Downey Jr.'s films, Iron Man, and so on, would be knowing also about Elon Musk, richest man, they say, in the world. And he has a large number of companies he owns, one being the SpaceX. And you can resonate with what he keeps saying, that only a couple of years back, what we have today in our world, it seemed it would be only a magic wand which could make it a reality. But today we all see the technology has made so much possible. The reason we are talking here, sitting distantly on this platform, and many more things. Very interestingly, I'm sure many would be aware that this International Space Station that we have, earlier the capability was only with Russia, to take the space expeditions. And the way India also is privatizing all its major sectors, including space sector and so on. And this is an example how SpaceX and NASA have collaborated. And today, the expeditions are going through this private company, SpaceX. And also, this International Space Station is all solar powered, And also would like to share, I can see there are students from colleges, even schools, who have joined with us. What would happen earlier was that when a space expedition would go in the space, all the hardware, that is the rockets, the boosters, etc., they would get wasted. So these expeditions were very costly affairs. After this private sector participation, today what is possible is that when the astronauts are sent, the space missions are sent to the International Space Station, all the hardware comes back and it's reused, which means it has become a very, very cost-effective affair. And no wonder now his, own company, which is, offering the space, private sector space expeditions as well. Similarly, to other companies, I feel like mentioning Virgin Galactic, which I'm sure many of you again would be aware of. Richard Branson owns that, and also Blue Origin of Jeff Bezos, who's the owner of Amazon. They are also offering the intergalactic travels. It's not only restricted now to earlier to domestic travels and then the international travels, and now it is travel to the other world, like to the other planets, which has become possible. And as I was mentioning, the entire International Space Station is powered by solar power. And I think when we talk of future technologies, this is the future, that as we go along, the entire planet Earth would also be, powered through renewable energy sources. It will be solar powered and so on. And a large amount of work has already gone into that. And you can also imagine the kind of change it would bring to a common man's life. When I say that, I mean how much the inflation would go down, because our dependency on the other countries for fuels will decrease if we are able to meet that. And now we have, as a country, given this challenge. Prime Minister has announced that by 2030, 50% of our electric installed capacity would be met from renewable sources. And I take pride in sharing with each one present here that these are a few examples to look at when we see our own state, Punjab. If some of you are not aware, we have world's largest single rooftop solar power plant in Punjab. It is in Dera Vyas. And also Punjab is the first state in the country which is offering incentives for the buildings which comply to energy compliant building code, compliance building code, which means the more and more energy saving buildings one can expect in future. These are the kinds of rebates that the state offers, and this would be something. At the moment, it will see it as we felt a couple of years ago. In fact, yesterday we were discussing about the minute-to-minute program of this event, and I shared with my team here that I can recall as a child, I have seen in India manual scavenging happening. In our own house, I had seen. And I remember this sweepress, the woman who used to come to collect shit in the morning. Sewage system wasn't there. I always wondered why she was a very short-tempered woman. I was a very small child at that time, living in my grandmother's house, and I vividly remember this woman who would be fighting, at the drop of hat, she would pick up a fight with anyone and everyone, and as I grew, I could recall that why she was so bitter. The first thing in the morning she had to do was this, collecting shit from people's houses, and how technology has brought difference, and to a common man. And here we can see I talked about us meeting 50% of our power requirement from solar power, from the other renewable energy sources. You will hear to one talk on hydrogen as well today. And India has come up with its national hydrogen policy very recently. So this in this picture, I can foresee, we all can foresee that in times to come, the rooftops of houses would be so smartly designed that they would be made of solar panels. We today see in a very ugly manner the solar panels fitted on the tops of on our rooftops. I think the roof itself, perhaps in times to come, would be of solar panels. The roofs of cars would be of solar panels. We would be able to overcome the challenge of Dr. Datta talked about self-reliant India, Atmanirbhar Bharat, the solar cells which we import as of now, in a big way. We would be able to develop those indigenously here in India. And I also foresee revolutionized transportation. The other day when I said we were together, Mudit and me, in a FICCI panel, he was sharing about the initiatives India is taking to bring e-mobility. About 3,000 crore investment having gone in, building all the infrastructure and the related ecosystem for e-vehicles, startups being promoted in a big way, venture capitalists coming up, and so on. And I also foresee that in times to come, the road network would be such that the e-vehicles would be able to charge themselves by just moving on those magnetic roads. That seems to be again a vision for the future, but I really see it coming perhaps in very near future. And 3 Indian states signed MOUs to facilitate the development of Hyperloop. And when we say Hyperloop, you can see this when the planes move in air, there is a friction of wind. But when we talk of hyperloops, they would be moving in vacuum, which means no friction at all. And we can then imagine the transportation would be faster, multi-folds, many times than what even the air transfer offers us in today's scenario. And when I mentioned about the solar power in the last slide, I also wish to share that India is the first country in the world wherein one of our airport at Kochi in Kerala is 100% solar powered. And when I say Hyperloop, and when I say e-vehicles, yesterday itself, Adar Poonawalla, who is the CEO of Serum Institute, he was tweeting. He said, Elon Musk, if you have not been able to somehow materialize this deal of acquiring Twitter, which he has already, then I urge you to come and invest in bring Tesla, which is his company, to invest in e-vehicles in India. And I assure you that it would be a very, very, what would say, remunerative, investment. So a lot happening. This is a priority of the government as well as private sector. And Punjab is also exploring the feasibility of Hyperloop transport, for a very busy sector that we have, Amritsar, Delhi, and so on. And also, when we talk of future technologies, the advancements in AI, IoT, blockchain is affecting almost every sector we name of: mobility, education, communication, agriculture. If I share briefly with you, India has already put forward its national strategy for artificial intelligence, made a budget outlay of more than 3,000 crore for semiconductors and promoting electronic component manufacturing. And also, very happy to share that India is also training 85,000 plus specialized engineers, building our human resource capacity. These are being trained by 100 plus state-of-the-art institutions across the country in these technologies. And there is a huge focus on 5G narrowband, and as well as its complementation with IoT, which would mean increasing the battery life, which would mean increasing the efficiency of networks. And you can see the global market size presently on the right-hand side of the slide, and it has been increasing in the, say, last 7-8 years exponentially. And here in Punjab, we have STPI Neuron, which is a which is a hub that is mentoring startups in these domains. It is working in tandem with business institutes like Indian School of Business. METI is supporting it. Harpreet is here. We have a Indo-Taiwan Joint Research Center in IIT Ropar. There is a Center of Excellence which Chandigarh University has also set up. They are focusing on AI's applications in agriculture. And also, this is a very unique initiative, first in the country. Punjab has set up a Punjab Road Safety and Traffic Research Center. It has come up at Mohali. There was an increase, and on an average, there was say about 11 to 12 casualties every day, because of road accidents. And then the Punjab government worked at identifying the black spots, brought in experts, and so on. So this could be reduced. And looking at the power technology can play in addressing this challenge, this center has been set up, and it's working in a big way on AI, ML, and IoT. And also, India is known for its defense system, strong defense system. The largest chunk of our R&D expenditure of India, which goes into various sectors, majority of which, largest chunk goes to space and defense. So India is a force to reckon with as far as defense sector is concerned. And now countries' focus is on building defense as far as data is concerned. It has taken giant leaps in data security. I would just share one example here. IIT Mumbai has come up with the first indigenous technology for semiconductor memory for the secure applications, and it has entered into collaboration with, it's a lab to fab, and only a couple of years back, lab to land was a phrase which was very common. Today, lab to fabrication or lab to fab is a phrase which is really gained popularity as we talk more and more of Atmanirbhar Bharat. So IIT Mumbai and our semiconductor lab here in Chandigarh is now manufacturing this semiconductor memory chip that IIT Mumbai has come up with, and it is estimated, it has yet to come into market, and large scale applications into e-passports, cashless transactions, and overall increasing national security can be foreseen. And a market size of about $140 million being expected out of this one single application. Again, US and China are way ahead when we talk of quantum computers. India has launched its national mission, set aside 8,000 crore budget, setting up 21 quantum labs and 4 quantum research parks across India. And IISER Mohali has also got a specialized center. When we talk of this field, these are the kind of applications: aerospace engineering, weather prediction. Earlier, when we talked of computation, we all were aware of these two binary, 0 and 1. That's how the computers work. But quantum computers bring in a new concept of 0, 1, as well as a combination of both. I'm sure many of you would have read in yesterday's newspaper Tribune itself a huge article saluting these 4 women, fantastic 4. They are being called today. I think that the example India has put forward in developing its own vaccine for COVID within 1 year, I think it's an unparalleled example of technology advancement, and the way we can see future in terms of providing healthcare to a common man in India is concerned. You can see these 4 women. Please go ahead and read more about them. These are, especially I would urge women present today on this forum. We have the director of National Institute of Virology, Pune, Priya Abraham. We have the head of Biosafety Level 4 lab, which is the first in Asia and the first in India, Pragya Yadav, again in National Institute of Virology, Pune. She's heading that. And Nivedita Gupta, who is the daughter of our own Dr. C.M. Gupta, who was heading IMTech Chandigarh and then CDRI in Lucknow. She, though being a medico, turned into research, and then, she is heading virology in Indian Council of Medical Research. And also we have Padma Priya, Director, National Institute of Research in TB, Chennai. How these 4 women, through their perseverance, their determination, have made possible the testing of Covishield, as well as bringing out our own Covaxin from India, possible within 1 year's time frame. And agriculture, I'm sure all of us present here take pride in how Punjab as a state had taken lead. The condition that India was from ship to mouth, which means the ship loads of food grain would arrive here from US, and we would feed our mouths. To being a food surplus nation, helping India become a food surplus nation as a result of technology advancement, the green revolution that we call it. And today we are, exploring end-to-end smart agriculture. To mention just 1 or 2 examples here, our Punjab Agro Export Corporation is deploying blockchain technology. We are a largest producer of seed potato, and to end, keeping a track of seed potato, be in terms of diseases and so on and so forth. Pegrexco is moving forward to deploy blockchain for that. AgNext is our emerging unicorn from Punjab, which is working on deep tech in agriculture sector, and flying agriculture, which is through drones, be it sprays of farm chemicals and so on, and also keeping a tap on every nook and corner, every inch of our farms. That's what the technology, drone technology, Kisan drones are making possible. And as far as industry is concerned, we all know Punjab is the hub of manufacturing. We have more than 2 lakh MSME. But India ranks, sad to absorb this, that India ranks 91 on the readiness level on adopting Industry 4.0. We really have to catch up on this front. But I will share a beautiful example, a classic example of one of our steel rolling mills here in Punjab, which our own, I'm sure Harpreet will share with you much more that IIT Ropar can contribute to. And I will urge Harpreet also to identify a few cases where we can make difference here. So this one case study, Royal Alloys, it's a steel rolling mill. And this is the picture you see on the left side. This is a before and after picture. The all pulverized coal all around in the industry. So much so they knew that the lifespan of an industry worker who works, who's at the helm of affairs as far as firing, loading raw material is concerned, he had a shorter lifespan. They knew that, that they knew they would die early. They are in this, they are in that's an occupational hazard, that kind of occupational hazard. And the industry tried to shift to PNG, piped natural gas, but they couldn't achieve the economics. So with the large number of technology interventions through large scale automation, My own team has been able to make it possible. And today, this is what industry looks like. Their next generation of industry owners want to come there. They've invested something to the tune of more than 1 crore, which they will reap back within 1 year, and then they will stand to benefit to the amount benefit by about 1 crore every year. And they are branding their steel as green steel as well. Our industry at Ludhiana is coming up with innovations like they are the second largest in Ludhiana's, for example, Hero Cycle, second largest in design filing as far as IP is concerned, with 3D printed bicycles and intelligent lights. And this is what I think will also drive future technologies. Climate change would also drive future technologies, maybe by making thoda difference, a very small difference, but they will have huge impact. If you see picture on the left, this is only a nozzle change in the tap, but it makes the water available in a fog spray form, which means you can imagine how much saving of water resources we can have by simply introducing one small tech intervention. And picture on the lower side of the left, we couldn't as a state imagine cutting down water on rice paddy sowing, but we are able to do it in a big way. We are reverting to we are shifting to directly sown rice. Technology was demonstrated only within the last 2-3 years, and now farmers are shifting it to DSR. If you see yesterday's paper, government also announcing the monetary benefits and other hand holdings if the farmers adopt to this. I think that's all from my side. And I'm really looking forward to today's speakers. And I'm so glad that young minds are listening to all the talks today, as they would be the ones. I remember some time back, Dr. Mashelkar saying that when nano was invented, nano car, was invented, he said today, besides making space in our garages for our drivers to park their own nano cars, we have to make space in our heart, that we can see that our drivers coming here on, to attend to his duty on a car. It has already become a reality. Everybody, a pan wala, a sabzi wala, having a mobile phone has already become a reality. And let's see how we can impact climate change by futuristic technologies, how we can make changes to lifestyles of people through future technologies. Thank you once again.
An interesting journey from where we were to where we are and where we want to be. Thank you, ma'am, for sharing with us all these forgotten sites and strengths of Punjab in future technologies. We are very privileged to have with us Shri Mudit Narayanji, Chief Technical Officer from Office of Principal Scientific Advisor, Government of India. Mr. Narayan has done his Master's in Public Policy from Massachusetts Institute of Technology. He has served for 7 years in World Bank, where he implemented several projects pertaining to efficient clean energy generation, transmission and distribution in several Asian and African countries, including India. He served as program director at the Atal Innovation Mission, Niti Aayog, where he focused on encouraging technology-enabled entrepreneurship. Mr. has contributed to several research papers, landmark reports, and opinion pieces in leading business newspapers on climate change mitigation. I invite you, sir, for your keynote address on trends in future technologies dissemination.
Thank you so much, and thank you for that kind introduction. I think a lot of the themes that I'll be talking about were reflected in Dr. Jatinder Kaur's presentation, and I'm glad to see that reverberation. So let me go to my slides quickly. I'll be taking you through my perception of how deep technologies or new age technologies are getting commercialized in the country, and how different pathways are being evolved, whether it is public private, or a mix of the two. And with a few examples, maybe we can have a bit of a conversation on how we see this kind of transition from the lab to land, including lab to fab, how this transition is happening, how it will, and my perception of what the evolution will look like in the next few years. So with your permission, I'll go to the slides. You should be able to see my slides. Can somebody please confirm if you can see my slides?
Yes, sir, we can. Thank you.
Great. So lab to land has been an aspiration, and it's an aspiration which India still needs to meet at scale, which is comparable to our country's ambitions. And what does lab to land mean? It is that if there's a new
Sorry to interrupt, sir. Please, can you please change your mode of display to full screen?
I am on full screen. Is it not getting shared on full screen? How about now? Are you seeing it on full screen
Better,
or
sir.
still?
So it's
Sorry?
better. Thank you. It's better, sir.
Okay, great. Yeah, so the concept of lab to land is that when there is a new scientific discovery or a new technological advancement in a laboratory, how can our citizens take advantage of that? And too many of us know, unfortunately, that we in our country missed out on the first three industrial revolutions. Broadly, if you think about them, the first industrial revolution was the internal combustion engine, the steam engine, or the entire steam revolution. The second was chemicals, which was again mostly in Europe. Third being information technology. We still don't make our own chips. I think all of us know that till very recently, most of the phones that we bought were imported. But hopefully for the fourth industrial revolution, we will be in a place to be able to lead and not just follow other countries. And that requires commercialization of new technologies. In the next few minutes, I will make the case that a lot of this is changing faster than we thought, and being led by startups of various hues. And India has also discovered a very interesting new pathway, which is public platforms for citizen services. If I was in a physical room, I would have asked all of you if there's anybody who has not used a UPI in the last 1 month. And I'm sure I would have found very few hands. And the UPI network has been a big success in the country. And there are other such platforms which are being built. The Open Network for Digital Commerce just got launched, I think, last week. The National Digital Health Mission, the National Livestock Mission. A lot of these are examples of public platforms or public platforms being designed by corporate and private entities for citizen services, which will help us leapfrog. And this is my favorite example of how far ahead India is when it comes to digital payments. And if you see on the left, in the middle is this less known entity called NPCI, the National Payments Corporation of India, which is owned in totality by all these banks whose logos you see around that. And it's an example of how all these banks came together to create a common platform so that any of us can send money to any merchant or any friend or any peer directly from our phones or online in a fraction of a second. And the ease and its stability and smoothness is reflected in how India has picked up digital payments far ahead of any other countries. And you see examples, countries like Korea and Thailand and Japan have been far ahead of India when it came to technologies and products. But this is one space where we really did move ahead faster than anybody else. You could take other examples such as mobile technologies where India leapfrogged, but that was not our own technology. This really was an Indian example of an Indian technology. But this was to some extent in the information space where information technology has been our strength. India has done well in the IT space. In the next few slides, I'll give you examples of some very interesting areas where India has done well. Let's talk about space. Dr. Kaur talked about how we're all following the series Rocket Boys and how the trajectory of taking rockets from our on bullock carts to being amongst the global space, the leading spacefaring nations in the world. We've seen that transition. And now this is my favorite example. Pixel is a company started by by entrepreneurs who graduated from college in 2018, from BITS Pilani in 2018. And that company has already thrown up a satellite, is planning to throw up 7 more within the next 1 year, I mean, within the next 10 odd months. And that kind of acceleration of technology adoption is really going to be the story of Indian technology and commercialization in the next space. That is not the only example. Many of us might remember that the first domestic COVID-19 test came out of a lab in Pune, which was at that time just 4 years old. It was called My Lab. The company had started at the end of 2016, and it was the first lab, the first startup to come up with a COVID test within a few weeks of the genetic sequence being available. Skyroot is another example which is now developing a cryogenic engine. And many of us are old enough to remember that cryogenic engines were denied to India in the early 90s due to a sanctions regime. And you know what? There are Indian startups, young Indian engineers who are now building cryogenic engines on their own. And I'm using these headlines just as a way of reminding us that these are companies that didn't exist when many of us started our careers, when many of us probably started school, and these are the companies which are now building this future. Ola Electric is another personal favorite. It's a company which is aiming to build 1 electric scooter every 20 seconds with 10,000 women working in the factory. Figures and numbers which we never thought would be coming from India. You all saw, I think, with a lot of excitement, the drone show at this year's Republic Day. And not many of you would know that this company didn't exist till about 3 years ago, and is still based out of IIT Delhi, and has shortened the timeline from the lab to commercially deploying it in front of all of you, in front of the nation. And that how the culture of taking your technology to the market through a startup really is booming in all of our IITs, all of our institutions. Idea Forge is a company which many of you might be aware of, has started developing and selling drones to the Indian Army. And this was a company which came out of IIT Bombay, IIM Ahmedabad, which had for 10 years very little success. And as soon as policy reforms happened in the country, between defense procurement, between drones and so on, the public platforms allowed them to expand very quickly. But these are not the only examples that we talk about. I think many of you would have seen this chart in the last couple of days listing out India's 100 unicorns. And this is a bit of a glib figure, the 100 unicorns, because you can, of course, make the case that only about 23 or 25 of them are profitable. But I see a lot of energy and a lot of enthusiasm in these companies to bring technologies to market. Sure, many of them are primarily IT or e-commerce and market spaces, but that is the beginning of how any innovation, any startup evolution happens. And whether you see Zoho on this, I've already talked about Ola and Ola Electric. I've talked about not talked about Renew Power, which is a very large renewable energy company. You see a lot of new innovations coming out of Zetwork. You see a lot of innovations coming out of InMobi. These are all companies which probably didn't exist even 10 years ago. And they are now starting to bring technologies of different kinds to market. And many of them are from the university space. And that creation of a methodology of bringing your technology to market from the university directly has a lot of potential, as we're already seeing in areas I mentioned earlier, like space, diagnostics, healthcare, and so on. But is the technology innovation that we are seeing limited to these fancy, glamorous areas like space? I would argue not. I have in front of you 4 examples of how technologies developed in India, and in most cases commercialized by startups, have started improving civic services, city and urban services in smart cities and in rural areas, so that all of our lives improved. Dr. Kaur talked about the unfortunate history in India where manual scavenging was existing in people's living memories. And you now have engineers, innovators creating robots to clean up those same sewage lines. And I hope very soon we'll be able to see some stories where children or grandchildren of manual scavengers are now actually creating robots to do the same task and making a lot of money out of it. So I think from a very unfortunate recent history to a more hopeful future is the transition that we are seeing in our lives. But that was one example, the Bandicoot. If you see other examples where Thane created a system to get all of its medical services online and to make sure that testing facilities reached its citizens. You have waste to wealth or plastic to diesel conversion plant coming up in Prayagraj, Uttar Pradesh. And these are examples of where public entities or public authorities like state governments, city governments, federal governments are working together with technology developers, technology providers to build India's future, to build the future of India's public services. And I'm talking about two areas which again Dr. Jitendra Kaur mentioned. I am very confident that in the near future, electric vehicles or the transition to electric mobility will have Indian champions. Whether you look at battery swapping policies which are being set up by the government, launch of the Amrit platform, availability of a map for EV charging. These public platforms are now creating many unicorns. Of course, I talked about Ola Electric, but you have some very innovative products coming out of companies like Zip. You have old companies like Hero Electric coming. And that future of Indian innovation built on a public platform of both policy and information and database has the potential of leapfrogging India from a technology follower, which we cannot deny we have been, to hopefully very soon a technology leader. The other area where I see immense amount of growth and domestic growth is Internet of Things. Our amazing engineers of various kinds have worked across factories, across construction sites, across civic services to connect this world very quickly. And I believe that just as how India saw the leapfrog of our UPI ecosystem, our IoT ecosystem is going to be just as world leading and just as transformative. We are starting to see a 4G user base of more than 820 million. That's almost 2/3 of Indians having a phone in their hand in some way. And that database is going, that data that is created is going to create the best template for AI, artificial intelligence related innovations. And I believe that the interface again between government and the private sector is developing the right opportunity, the right fertile field for the seeds of innovation from these innovators. And I quote the Nirmala Sitharaman, who said that the government, the Honorable Finance Minister, who said that the government will promote the use of AI in a big way to modernize all aspects of education, banking, agriculture, transport, and so on. And that is the kind of change that you're seeing in your government, in your future. So where do we go from here? What lies ahead? I believe that as we've seen so many examples in our lives, the future of development of our country lies with the development of new technologies. In the last few years, we've seen a near saturation of basic services like electricity, roads, cooking gas, telephones in almost all villages, all households. We used to be a very deprived country when it came to saturation of these services. But in the last few years, we've seen that saturation. And for anything now to build on this will require new technologies. We have an amazing resource of skilled manpower, which is adept at using technologies. And this will provide the right building blocks for us to be able to take the lead in many of these sectors. And when I say take the lead, it is not just about supplying Indian citizens. I strongly believe that just as pharma and IT are two sectors where India has taken the global lead, there are other sectors where we will be in the forefront, whether it is electric vehicles, whether it is artificial intelligence, whether it is drones, space. These are some sectors where we will not just be serving our own citizens, but becoming the suppliers for new technology, new products, new solutions for the entire world. And that is where I am confident that India's space or India's place in the next industrial revolution is confirmed. Those are my points. Very happy to take any discussion or questions that you may have. Thank you.
Thank you, sir, for sharing how new age tech startups and governance are accelerating the technological evolution of this nation. Moving forward, we are extremely fortunate to have Mr. Patrick Herbert, Honorable Consul General, Consulate General of Canada in Chandigarh. Mr. Herbert is a Canadian diplomat with over 25 years of experience in government, including 16 years in different countries. He has strong interest in international peace and security, environment issues, and sports, with having run his first marathon in Stockholm in 2015. Mr. Patrick has served in France, Serbia, Sweden, and South Korea before coming to India. I take a great privilege and honor to welcome you, sir, and invite you to share your thoughts about bilateral relations on science, technology, and innovation.
So thank you so much for this kind introduction. I must say it's quite humbling to be on a program with so many eminent scientists today, but I would like to address my congratulations to the Government of India and the Government of Punjab for bringing together so many participants for this important discussion on science and technology. As a diplomat with degrees in political science and international relations, I'm not in a position to contribute to the science and technology knowledge being shared this morning. However, as someone who strongly values the contribution of science and technology in finding solutions to the challenges that we all face, I would like to spend some time very briefly this morning to introduce some of the key partnerships between Canada and India on science, technology, and innovation. But this is not a new partnership. Indeed, Canada and India signed a joint S&T agreement in 2005. And at that time, the Canadian minister said, and I quote, "Under the new agreement, Canadian and Indian researchers, universities, and businesses will work more closely to discover new ideas and products," end of quote. And we've gone a long way since the agreement was signed in 2005. And in fact, Canada and India will hold their 7th meeting of the Canada-India Joint Science and Technology Cooperation Committee later this month. And the last meeting of this committee, that was before the pandemic, it concluded with the signing of a joint statement to strengthen collaboration in areas such as researcher mobility, nanotechnology, health research, sustainable infrastructure, and clean tech, among others. But in addition to these very important discussions between policymakers from both countries, we in Canada have put in place a number of programs to support concrete ST&I cooperation with India. And I would like to mention a few very quickly. The first one is known as IC Impacts. This program was launched in 2013, and it brings together Canadian and Indian researchers, companies, and communities to address socioeconomic challenges and support high-impact, application-oriented research that meets the sustainable economic and community development needs of both countries, both Canada and India. IC Impact has so far completed 74 projects covering areas like water management, public health, sustainable infrastructure, technology, etc. This program has also trained over 1,000 highly qualified Indian and Canadian personnel. And just recently, IC Impact signed an MOU with Guru Nanak Dev University in Amritsar in the field of food security. I would also like to mention the Canadian International Innovation Program, or CIIP. And through this program, Canada provides up to $1 million Canadian dollar every year to support industrial R&D cooperation with India. I should also mention that we also have strong ST&I cooperation in the agriculture sector. The Canada-India Joint Working Group, established by our two ministries of agriculture in 2009, so more than 10 years ago, have supported various S&T cooperation, including for cereals, pulses, oil seeds, but also on our respective response to climate change. And there are many more examples of cooperation between Canada and India, but I'm conscious of the time now, and I don't want to take too much time during the program, but I would be happy to provide more details offline to those of you who may be interested. However, before I conclude, I'd like to say a few words about research mobility. In 2019, an organization in Canada called MITAX and the Shastri Indo-Canadian Institute signed a 3-year agreement to support the bilateral mobility of undergraduate and graduate level researchers. And this agreement builds on MITAC's existing partnership with the All India Council for Technical Education. And even during the pandemic in 2020, MITAC supported over 500 summer virtual research internships with Indian students and is now on pace to support over 300 in-person internships for 2022. And these students who participate in the program are the leaders of tomorrow. And I'm glad to see that the STNI cooperation between Canadian and Indian researchers starts from the very beginning of the career. And I'm also glad to see so many students on the program today. Thank you for being with us. I certainly hope that this cooperation that starts at the university level will continue throughout your career. And when I look at the agenda for your conference today, I see a lot of topics that are of interest to both Canada and India. And that leads me to see strong potential for future cooperation. So thank you again for having me. And please, please do not hesitate to reach out to me should you be interested in being part of the Canada-India success story on science, technology, and innovation. Thank you again.
Thank you, sir, for putting light on dynamics of Canada-India relationships in regard to science and technology. Next, we have with us Dr. Harpreet Singh, Professor of Mechanical Engineering, IIT Ropar. Dr. Singh, known for his research in surface engineering, biomedical coatings, and much more technological innovations in field of mechanics. He has received Young Scientist Award, Career Award for Young Teachers, and Maharashtra Award for Outstanding Research Work. To his credit, he has completed several CSIR, DST, and AICTE-sponsored projects. He has authored more than 60 papers in international and national journals and conference proceedings. I invite you, sir, to share your views on cold spray as an alternative additive manufacturing process. Sir, please.
Thank you very much, Lokita, for this introduction. So let me start sharing my screen. Please confirm if you can see my screen and my voice is audible. Hello? Hello?
Yes, sir, you're audible.
Yeah, can you see my slide?
Not yet, sir.
Oh, let me see. But it says it is sharing, right? How about now?
Yes, sir, it's in the process.
Yeah, can you see now?
Yes, sir.
Okay, I will put it into the slide mode. Is it now good?
Yes, sir.
Okay, so let me start my talk. So first of all, thank you very much for giving me this opportunity to, talk about this topic of cold spray. Especially in front of a very young audience, I could see some of the people in the box that some very young faculties and students are attending this talk. And of course, there are other side, we have some policymakers and very senior people from Government of India and Government of Punjab. So I would be talking about cold spray as an alternative additive manufacturing process today. Now, why we talk about manufacturing so much? The first of all, it's very generic remark that manufacturing industry is kind of backbone of any economy. So if you see even this global economy, so 16% of this global economy comes from manufacturing, and you can see that almost all countries, they are enjoying major share from this manufacturing. And the exciting example is of China, where 40% of its GDP comes from manufacturing, and that's why we are talking about the manufacturing here. And when we talk about the manufacturing, we can't forget about mentioning the additive manufacturing, because additive manufacturing is one of the 9 pillars of what we call industry 4.0. Some speakers were talking about that. And this additive manufacturing is kind of one link in this whole industry 4.0 revolution, where the things will be actual printed, right? You can always design things on paper, but at the end of the day, you need some product in your hand. So that is where this additive manufacturing will help us. And when you see the business, additive manufacturing is growing like anything. So the CJR, what we call 20%, 27%, you can see the growth here actually. And this aerospace and defense sector, they again are registering or expecting a growth rate of 26 in their business. And another very promising field for our 3D printing or additive manufacturing is medical devices, and there again you can see a tremendous amount of growth rate. So that's why additive manufacturing has been talked of the town quite often nowadays. So what is additive manufacturing? So I'll spend since time is very limited, so I'm not going to discuss in much more details here. The only thing is which we should know about additive manufacturing is that we are adding something here. Earlier, when we have to make some part, we use subtractive models where you will take a raw material and then you will shape it into the final product by removing the material from the belt or the raw, that. But here, what we are doing, we are adding things in layer by layer to make the final product. Okay, and that's what is all about additive manufacturing. So you're adding layer by layer to bring your product. So there are certain stages here. So you have to have a very nice CAD model. For example, if you want to print this cup, you will first make its CAD model. That means you make it's a 3D drawing, and then you will convert it to what they call STL file format, which is readable by most of the additive manufacturing machines. And then you can set the machine, you can print this, and then there is sometimes there is some kind of post processing to be done, right? And then you can use this for your final application. So the exciting thing about this is that a lot of logistics has gone away from here, and you can simply print your parts now, without using much more logistics. Now, then, what are the technologies which are available right now? There are several technologies, and of course, this is very open field. People are inventing different ways of doing additive manufacturing. Now, the thing here is that in order to do something layer by layer, you have to have some kind of mechanism, some kind of media by which you can attach these layers to each other. Okay, so there we have the heat. Heat can come from some e-beams. Okay, it can come from your lasers. Okay, but there are some other routes also which we call stereolithography, where we typically cure our polymers to give the shapes and so on. And we have laminated object manufacturing, another approach where you are layer by layer, your laminate your papers are being attached to each other with the help of some adhesives and so on. Okay, but today, what I'm going to talk about is not about these conventional technologies. Of course, they are very popular. They have their own advantages. But then, as I said, there is always, strive. We engineers always strive to bring something new on the table, which may have some kind of added advantages in one sense or other. So there we are now talking about this cold spray process. Now, what is cold spray process? Now, this cold spray process is I would say, rather simple process where, that where we have the metallic powder particles. So we use the powder, to make our final product, which is also a case in most of the additive manufacturing technologies. So, but here what we do, we are propelling this powder through a very special kind of convergent divergent nozzle, which we call, right? So this nozzle has been specifically designed to achieve supersonic velocities of some gas. Here in this case, most of the time we use some cheaper gas like nitrogen. So this nitrogen can be accelerated through this nozzle, which those who are in mechanical engineering, they will understand this, that if we have a converging diverging nozzle, we can always accelerate the fluid to supersonic velocities, means we are more than Mach number 1. Now this is one thing. Now why I'm accelerating this gas too much high? Why? Because I want to propel my powder particles at very high velocities so that they can move at supersonic velocities, and then they can strike on the surface where they will stick as the layer. So that's what we are doing here. So we are taking the powder particles, we are heating them just to remove the moisture. It's not that we are melting them or something like that, as we used to do in the thermal spray. So here the beauty is that we are doing everything in solid state. Now, so one, we are propelling our powder particles and we are propelling our gas as well. And we heat this gas to some extent. Why we heat this? This is about thermodynamics, because if you don't heat your gas, when it will expand through this nozzle at the throat, there is this kind of sudden expansion, and your gas can get cooled and you may feel choking or something like that. Another thing is that when you heat the gas, it can achieve supersonic velocities easily, because that velocity can be increased for the lighter gases. So this is a very brief about cold spray process. This is a typical nozzle, kind of a schematic. I would say it's the actual kind of gun, which you can see we call it gun also, uh, because we are shooting these particles at very high velocity towards the substrate. So there you can see this nozzle here, and we have this whole chamber. Now this is a cold spray gun at IIT Roper. So this has been established as a national facility at IIT Roper with some funding from Government of India, and it's now being used as a kind of national facility. Several vendors or several people, students, academicians, universities, people, they are coming to us to use this facility at IIT Roper. Okay, so let me show you a very small video of this operation. So you can see this is the gun and the nozzle. We are getting these particles here, which are being deposited on this surface. Okay. Now, how they are getting deposited, that is a subject matter of maybe half an hour. So I'll try to comment on that if we get the time. But the point here is that as soon as you can see this layer by layer, they are forming it. Okay, so they are making layers of that material on this target material. Now, conventionally, this cold spray has been used for depositing small, thin coatings of the order of, say, a few microns, or sometimes even 1 mm and so on. But then people thought, why not to keep on depositing material layer by layer? And that is where the idea of using this surface engineering technology for additive manufacturing emerged, right? So what would happen if I don't stop, depositing, say, 2, 3 layers? If I keep on depositing the layer by layer, I can achieve very, thicker deposits here, and then I can take those deposits from this substrate and can use them for or as a standalone geometry. Another thing is that since I can manipulate this gun through this robot here, so and I can also rotate my job, so I can achieve some kind of relative motion between the job and this this jet of your particles. So I can prepare some kind of different geometries, standalone geometries, and then I can use them as the final product. Now this is about the capabilities of cold spray. Now, here if you see, we are not talking about surface engineering today, because traditionally cold spray has been used for making coatings, very high quality coatings for several applications. In fact, IIT Roper, we have done this surface engineering for hydroturbines and for boilers and biomedical coatings as well, and some other applications are there across the globe as well. But here we are more concerned about this additive manufacturing. So additive manufacturing, it can bring some kind of near net shape manufacturing. This is one very strong advantage of this. Why you use it, I'll compare it with laser and other processes also in a minute ago after this. Another application is repair. Okay, so these two applications, they fall under additive capabilities of our cold spray. Now then, what kind of materials we get? Whenever you will talk about any additive manufacturing technology, or for that matter, any technology, manufacturing technology, people will ask you what kind of materials we can process, right? Now here, you can see that we have a diverse range of materials, right from pure metals. So we can do the coatings or additive manufacturing through this using this material of aluminum, copper, and so on, and alloys as well, refractory materials, metal matrix composites is another very exciting application of this, that you can deposit several composite materials by a cold spray process. And those who work in materials, they will know that how much these metal matrix composites are valuable in our several engineering structural applications and so on. And of course, addition of metallic layer on carbon fiber composites. This is again very nice capability of this process. Now the question comes, why do we need to use this cold spray for additive manufacturing when we already have some kind of application established processes for cold spray? Sorry, additive manufacturing. Now let me tell you some of the advantages which are very interesting, and that's why people are exploring this technology for additive manufacturing. Now, first of all, there is absence of thermal stresses. Suppose I make a part through laser melting. So in laser melting, what we do, we have the powder, right, and then we melt it. Now when you melt it, that means it will contract, okay, and there will be another layer on it which will again be melted, and then again it will try to contract, but the previous layer will not allow it to. So there is always kind of thermal stresses, what we call residual thermal stresses, present in the materials by which are being printed by our conventional additive manufacturing process. But the beauty of cold spray is that there are no thermal stresses. Why? Because we are not melting the powders here. It's a solid state process, which means that you are not going to melt the particles, rather you are pushing them with very high velocity towards the substrate where they deform. Okay, there's a lot discussion on that, how but time is so much that I can't explain that. So in that case, we are not facing any kind of thermal stresses, rather the material is being pushed with very high velocity and it is deforming on the surface. In doing so, what happens is there are residual, of course there are residual stresses, but those residual stresses are compressive here. Now those who work in mechanical engineering, they will know that any type of residual compressive stress is quite helpful, especially when we have these fatigue applications. So that is one advantage here which we have. Another thing is more refined homogeneous microstructure. This is another strong point of cold spray, that when you do the coating, so what you see is that the particle is coming at a very high velocity, as I said, like Mach number 2 or 3, and when it goes through a very small distance. You have already seen the video. In that matter of less than seconds, microseconds, and so the particle comes and deform on the surface, and deform and then solidify on the surface. Now in doing so, you get very refined microstructure. Now here what happens is that you don't have any time for growth, right? So if you see a typical cold spray deposit, you will see a very the microstructure will usually be refined when you compare it with the feedstock material, right? Low oxide content as well as porosity content. So this is another very strong point, that whenever you have temperature in your process, there is always a kind of risk that you are getting some kind of oxidation, because most of the material, they will oxidize as soon as you will expose them to the temperatures. So here, since temperature is very, very low in our process, so there is no possibility of oxides. And of course, since you are consolidating the material very nicely on the substrate, your porosity levels are also very less. Another point is that depositing temperature sensitive material, as I said, because we are not exposing them to very high temperatures, though, so their metallurgy will remain intact. Another beautiful advantage of cold spray is that materials with very high thermal conductivity and reflectance, they can be also worked upon. Now the problem with the laser based processes is that if the material is reflective, right, then you may not get the advantage of or it will be difficult to heat the material. right? There are some ways, but still you have to make some extra arrangement for that. But in cold spray, we are not bothered about it. Similarly, thermal conductivity also poses some kind of challenges. If the material is having high thermal conductivity, your laser will not be allowed to give you the focused heat on a localized area, because it will be dissipated very fastly, and you will see some kind of problems. Okay, so these are some of the advantages. I'm not going to go in all, but overall, another thing, since we are talking about the sustainability aspect of it, let me not forget about, tell you that this process is environment friendly, because temperature is a very big culprit as in our manufacturing, right? As soon as you raise the temperatures, you see a lot of problems, right? All fumes and other logistics and kind of stuff. So here, since we are working in solid state, so this is another very attractive feature of cold spray. In fact, one company came to me only for this reason. They say, "Sir, we are being exposed to these environment restrictions. So can we use your cold spray, because we have to use some sustainable manufacturing technology?" Now, what is that? So at the same time, I'm singing songs for this cold spray. What is the disadvantage? Disadvantage is in terms of the complexity of shapes. So I can't compete with, say, selective laser or selective laser melting process in terms of making complex shapes. So here only simple shapes can be made easily, not very complicated. So that is something which you have to keep in mind. I will skip this for the time being, because only one comment, that there is something known as critical velocity, which has to be achieved in cold spray, right? It's not that you will take a material, you will put material in the gun and you will deposit it. No, you have to do some kind of experiments. There are a lot of experiments, or sometimes we use some kind of simulation techniques to arrive at that critical velocity, right? So that is something. Yeah, this is again, we don't have time, but this is about the bonding mechanism here. That my bonding can be two types. One is mechanical bonding, that means particles are getting stuck on the surface, or metallurgical bonding, that means there is some kind of interdiffusion between these particles, and so on. But this is a kind of long discussion point which I can't do. So let me quickly show in the last minute where are the applications, some of the actual applications which people have tried. Now this is, you can see, this is a freestanding bi-material hollow shaped permanent magnet fabricated from this one. So this is some shape which has been prepared by cold spray. So similarly, we can have this also, multi-layered titanium. So see, one thing is that here even materials with different chemistries can be worked upon. Okay, that's another interesting feature of this, because in the earlier processes you will face some problems. For example, when I mix two powders in laser, there is always problem, because one say we have aluminum and silicon carbide, right? Both have different melting points. Okay, so they will cause some kind of problems to you. But here, since we are propelling everything and we are getting things stuck on the surface, so we are relatively easier in this cold space. So this is another some product which have been made by cold spray. You can see all these processes here. This is wholly made by copper flange has been made by cold spray, right? So see, 50 to 60 thick deposition has been done successfully here. So another, this is the repair application. So let me tell you why repair is so important, especially in aerospace and other applications and aeroplane applications or automobile. There are certain parts which are very costly actually. Okay, and every part is prone to some kind of damage. So it is always good to repair them rather to replace, because some parts are really very costly. For example, if you talk about gas turbine, one blade is a million, kind of very costly, right? So there people are using this cold spray very nicely. So these are some of the examples. I'm really short of time, so you can see some of these exciting applications. Joining is another important application. Making some kind of standalone. Even this cold spray has been used to make sputtering targets, which are again very need to be very pure materials and so on. Have been done. This is some work which we have done. In fact, in IIT Roper, we are doing some work also. So we had deposited very thick layers of very difficult materials which are not that easy to work. But I can't disclose much details on that because this is something we are doing with GE. So these are the parameters, and there's a lot of application opportunities for this technique. And I think I should, in the respect of time, I should say now thank you very much. If there are some questions, I will be happy to answer, or else you can always email me. Thank you very much.
Thank you, sir, for giving deep insights to technology. And we are happy to note that how these technologies are being offered to industries and innovators for its usage, leading to better and environment-friendly processes. Next, I would like to invite Dr. Amandeep Singh Oberoi, Assistant Professor, Mechanical Engineering at Thapar Institute of Engineering and Technology, Patiala. He received his PhD in Mechanical and Manufacturing Engineering Royal Melbourne Institute of Technology, Australia, and he was awarded exemption grant under the Commonwealth Government Research Trainee Scheme and PhD top-up scholarship from Victorian Brown Coal Innovation Australia. He has more than 10 years of work experience in industry, teaching and research. Dr. Oberoi has published around 30 papers in various journals and conference proceedings. Sir, I invite you to share your views on electrochemical hydrogen storage devices. Sir, please.
Thank you, Lokika, for the introduction. Let me share my screen straight away. I hope the screen is visible to everyone.
No, sir, not yet.
How about now? Is it turning up?
Yes, sir, it's in the process. Yes, sir.
Thanks for confirming. Okay, so let's start. I would like to start by extending my sincere thanks to the organizing committee for inviting me for this talk on electrochemical hydrogen storage devices. The introduction have already been given, so I'll jump on to the content straight away. What I'll be covering up today is I'll be talking about the SDGs, which are Sustainable Development Goals set by the United Nations. Then I'll speak upon green technology, a bit of it. Then to the main topic, which is hydrogen as a future fuel, how it could be produced, and what are the current storage techniques, what are the future storage techniques that will be helpful. And then I'll show you the research side of the hydrogen storage. I understand that there are in the audience, there are students from the college, from the bachelor level, from the master's level. So I'll start with showing up this screen, which is quite popular and quite commonly known. These are the 17 distinct sustainable development goals being identified by the United Nations. I am showing this because our research group is closely working upon the two and how hydrogen is being mapped with these SDGs. We are particularly focusing on the Sustainable Development Goal number 7, which says affordable and clean energy, and number 12, which says responsible consumption and responsible production. And hence, we are working on green hydrogen. Now, I'll start with the question. Since many students are there, I would like to start with what is green technology, what actually green technology means. Because sometimes we brush upon on the advanced things first, and the people sitting in the audience, they do not know about the basics. So this is just one slide to show what green technology really means. So it's a encompassing term which deals with using science and technology in order to protect the environment. In layman language, we could say that all the technologies, all the processes, those are eco-friendly or environmental friendly. They are referred to be as green processes or green technology. Now, energy efficiency, recycling, health and safety concerns, renewable sources, and many more, these all go into the making of green product or technology. Say, for example, there are already established technology or already established processes. So if by chance you increase the efficiency, if by research you increase the efficiency or you decrease the fuel consumption, it is referred to as the greener or eco-friendly technology or process. Now, why hydrogen? Why hydrogen has become a buzzword across the globe? Why people are really interested in hydrogen? We have been listening to this word for more than a decade now. It has gained a lot of popularity, but let's understand why people are really interested in hydrogen. A very fundamental periodic table picture is on your screen, and if you see, the hydrogen sits at place number 1. This is where it is. So the elemental information about hydrogen, I'm sure many of you already know about this, but very quickly I would like to brush up these things. So hydrogen is an element which was discovered in 1766 by Henry Kendish, and it is of the periodic table. It is referred to as a diatomic nonmetal. It is from the category of diatomic nonmetal. Its isotopes, which are popularly known as a single H or double H, which is H2. No allotropes. And if you focus upon the density, it's very low. Density is 0.000082 grams per cubic centimeter. Atomic number 1, atomic mass 1.00794, symbol is H. So this is what hydrogen is. Hydrogen these days is referred to as a zero emission fuel. Let me tell you why. Zero emission, as the name suggests itself, when it is burnt in the presence of oxygen, it emits nothing. It does not emit anything. So that's why it's known as a zero emission fuel. But the hard part is its emission or combustion, it's spontaneous, it's uncontrolled. So that's why people are blending it with the conventional fuels to make it combustible. Beside fuel, it is also recognized as an energy carrier. Not necessarily that we have to burn hydrogen all the time, but it's a beautiful energy carrier. I'll show you how in the upcoming slides. Okay, hydrogen, if it's a fuel, let's understand about its energy content, how powerful, what energy it has got, how powerful the hydrogen is really. So the energy content of a hydrogen is described in its lower or higher heating values or calorific values. The lower heating value of hydrogen, this is 33.33 kilowatt hours per kg. That means if you burn hydrogen, a kg of hydrogen, it is capable of giving you 33.33 units of power or electricity. And in terms of volume, a nanometer cube of volume is enough to generate 2.78 units of power. So the heating value is that it can generate 9.41. Nevertheless, 33 is for sure it generates. And on volumetric side, on base of higher heating value, it can generate 3.28 units. Now, if you compare it with the gasoline, that is conventional fuels or petrol, the energy content that is being produced by just a small nanometer cube of hydrogen volume, that is equivalent to what is being produced by 0.34 liters of petrol or gasoline. So that's why, because of its immense energy content, because of its light weight, everyone is now chasing up for hydrogen. All the countries have set up their hydrogen economic goals. In the earlier days, hydrogen was only used to be used in the space SLVs as a fuel, the liquid hydrogen, because of its low atomic weight. Okay, now ask yourself whether, now you know what hydrogen is, you know what green technologies are. Now ask yourself whether all the green technologies, they are sustainable. When I say sustainable, sustainability has to deal with what we take out of this planet, resources, and what we give back, how we replenish the resources. It's just not, taking out the resources, consuming the resources from the planet and putting nothing. That's not sustainability. Sustainable is how you replenish the resources that are being used up for your current needs. So whether all the green technologies which are currently available or known to the mankind, whether they all are sustainable or not, but the answer is pretty words are not always true and true words are not always pretty. So in other words, not all the green technologies which are known to us, they are sustainable. Why? Let's understand from the battery point of view. You see these lithium-ion batteries, lithium polymer batteries, lead-acid batteries. Are these a sustainable solution? Again, the answer is no. I tell you why. Do you know what's the carbon footprint of a battery, of a lithium-based battery, be it lithium ion or lithium polymer? It is estimated that it produces 1 ton of CO2, carbon dioxide emission, per ton of lithium carbonate production, which is the main constituent of the battery. 1 ton of CO2 per ton of lithium carbonate, which is being produced. Another problem with the batteries is the batteries, these all are self-discharging. You charge up the battery, you do not use it for a couple of hours, you'll see the amount of electricity that you have stored, it will be reduced automatically. These are self-discharging. They emit toxic fumes. The bigger problem, or the biggest problem, I would say, is the recycling. Lithium batteries, they incur high cost, huge cost as far as recycling is concerned. It is estimated that recycling a lithium battery, it costs around 5 times money than original production of the battery. So no one is really interested in recycling the lithium. Lest plastic parts, electric terminals, the joints, these all can be recycled. They are being recycled currently, but lithium literally is not being recycled. So eventually we are converting this planet into a lithium dump because all the lithium batteries after the end of the life, they just end up in the dump. So what's alternate? So hydrogen might be the solution. Hydrogen has already been recognized as a future fuel. Why? Here is the table to justify that. Just have a look on this table, which gives you the conventional fuel as well as the reversible hydrocarbons. So wood, coal, petrol, diesel, natural gas, these all are the conventional fuels. Reversible hydrocarbons is also known to the mankind, but not as a fuel. And I'll draw a special attention of all the audience to the bond energy. These all are the complex chemical bonds of carbon and hydrogen, be it the wood, be the coal, petrol, or all the products. Now, if you see the bond energy in the coal, bond energy of CH, carbon and hydrogen, it's around 400 kilojoule per mole in petrol, so almost same in natural gas. But if you see in reversible hydrocarbons, it's quite meager. It's quite small, only 30 to 50 kilojoules per mole. So, which means it is easy to break up this bond and extract hydrogen, which is already bonded with carbon in the form of reversible hydrocarbon. So again, if you see the extreme right column, it says the heating value or calorific value of all the fuels. So wood, when you burn 1 kg of wood, it gives you out 22 megajoules of energy. Coal 33, petrol 43, natural gas 54, but have a look on a hydrogen. 142, it's almost 3 times than petrol. Diesel has got somewhere around 46. So that's why the hydrogen is very, very important for the future. As I said, hydrogen, the combustion is spontaneous, it's uncontrolled, but it is also being used as energy carrier. Why? Because it produces zero emission at the point of use. It can be stored, it can be transported at high energy densities and as a liquid or as a gas. It can be combusted, which has got some safety issues associated with it, or used in fuel cells to generate heat and electricity. And it produces pure water as a byproduct of fuel cell. If you use hydrogen, it depends upon the purity and the oxygen. Now, the main thing, how to produce and how to store the hydrogen. Basis on the production processes of hydrogen, hydrogen has been categorized into these 8 distinct categories as green hydrogen, turquoise, yellow, blue, pink, purple or red hydrogen, black and gray hydrogen, white hydrogen and brown hydrogen. What we are aspired for, what we are looking for, the maximum efforts are being made to achieve the green hydrogen, because rest all, they are already available in the market. Now, green hydrogen, what it is, hydrogen produced by water electrolysis or dissociation of water using electricity from renewable sources in particular, that is either hydropower or wind or solar, and does not emit any carbon emissions while the hydrogen is being produced. This particular hydrogen is referred to as green hydrogen. Turquoise hydrogen is hydrogen produced by the thermal splitting or methane pyrolysis. Instead of CO2, solid carbon is being produced. That's why it's called turquoise. Yellow hydrogen is produced by water electrolysis, but the electricity which is used in water dissociation is coming up from the national grid. Blue hydrogen referred to the hydrogen in which CO2 is pressed or repurposed before liberating it into the atmosphere. Hydrogen produced from electrolysis using nuclear power is referred to as pink, purple, or red hydrogen. Black or gray hydrogen is extracted from the natural gas by SMR, which is most commonly used in today's world, steam methane reforming. White hydrogen is a byproduct of industrial processes like refineries. And brown hydrogen is extracted from fossil fuel using coal or using gasification. So again, I repeat, what is the ideal thing we are looking for is the green hydrogen, production of hydrogen from water dissociation, but the electricity coming up from the renewable sources. So coming up, conventionally, the hydrogen storage, hydrogen is stored as a compressed gas. Okay, it has shown some acceptable figures of gravimetric and volumetric energy densities. That is the amount of energy being stored per unit mass of the storage is gravimetric energy density. Amount of energy stored per unit volume of the host material is referred to as volumetric energy density. But of course, if you want to increase the gravimetrical or volumetrical energy densities, that comes up with a penalty in the form of, energy expenditure. Like if you intend to store hydrogen as a gas, the high pressures as high as 350 to 700 bars are required, and you need to run the compressors, and again you need to consume the electricity, and that electricity you don't know where it is coming from, either from the grid or from the renewable, you don't know. Okay, but storing hydrogen as a gas does incur some energy expenditure. Same is the case with the liquid gas. Since it's a quite lightweight element, it can atomize very easily. So if you want to store hydrogen as a liquid, you need to maintain the cryogenic temperatures. When I say cryogenic temperatures, so temperatures as low as 20.28 Kelvin. So if you want to reduce the temperatures to cryogenic levels, you again have to deal with technical complexities and the high cost, because again you need to use the refrigerants, you need to use the compressors, then the expanders, so on and so forth. Now also the gas and liquid, they do have got some safety concerns if the hydrogen leaks out, okay, because as a liquid, if it leaks out, it will atomize very quickly, will mix up in the air. And gas, if it leaks out, again it will mix up with the air. It's no harm to the environment, but if it catches a flame, it can cause disaster. That's why the safest form of storing the hydrogen is as an electrochemical compound or a chemical compound. It's termed as electrochemical hydrogen storage. This is the core area where we work in. Now let me tell you the electrochemical hydrogen storage. It's possible by two ways. It's called physisorption and chemisorption. Physisorption is called physical adsorption. That is storing the hydrogen in a physical form. And chemisorption means, storing the hydrogen as a chemical compound when it reacts with the host material and form weak chemical bonds with the host material. Of course, these chemical bonds can be detached. Now, this is the conventional way of producing the green hydrogen from the renewable source. You can see on the left side, there is the sunlight, the sun, which is powering, which is giving the light to the solar PVs, solar photovoltaics. Solar photovoltaics are consuming the light, and that light is being converted into electricity. This electricity, which is produced from the solar photovoltaics, this is used to power the electrolyzer. Electrolyzer is again an electrochemical unit which consumes the electricity and splits the water into oxygen gas and hydrogen gas. Now, the oxygen gas and hydrogen gas at STP, standard temperature pressure, will not give you the acceptable figures of gravimetrical energy storage densities. Now, if you want to store some good quantity of hydrogen and oxygen in the cylinders given, you need to compress them. So you need to have oxygen compressor and a separate hydrogen compressor. Then you need to store it in the O2 cylinders and the H2 cylinders. When you're going to use it back in a fuel cell is nothing. It's an electrochemical unit which consumes the oxygen and hydrogen. Then it reforms water and gives you out electricity. I repeat, it's an electrochemical unit, the fuel cell. It consumes oxygen gas, hydrogen gas, Then it has got some catalyst loading inside it, which splits hydrogen into ionic form and allows the electrons to pass through the electrical circuit, which is electricity, and gives out the water in return. It reforms water by combining oxygen and hydrogen. Now, this is the conventional system of producing and using hydrogen back into fuel cell. You can see there are a number of equipments which are there in the process. This incurs the low round the trip efficiency. When I say round the trip efficiency, this is the trip of electricity that we are counting. The electricity moving into the fuel cell, into the solar PVs and then to the electrolyzer, being converted into the gases, getting stored and then reusing it to fuel cell to give you all the electricity. So electricity in to electricity out, this is termed as a round trip efficiency. Now, in the conventional system, there are so many equipments that the round trip efficiency of the system is very low. So what researchers or the research desk, they have proposed is, that's why I'm now taking you to the research side of hydrogen storage. Now, what they propose is, they have combined the two separate unit of electrolyzer and fuel cell into a single unit. It's called URFC. URFC stands for unitized. Unitized means the two units united into one unit. Regenerative fuel cell. Regenerative fuel cell means in a one side, in a one go, it acts as an electrolyzer to split water into O2 and O2, O2 and H2. And when you reverse the polarities, you disconnect the power source, you start drawing the current, it start running as a fuel cell in the opposite side. That means the gases which you have stored, it start consuming the gases and start giving out the electricity. So a single unit that can run as electrolyzer as well as the fuel cell, it is termed as a URFC. It's still on a research bench. It has not been commercialized yet. It has not been produced on a commercial scale yet. So this has improved the round the trip efficiency because the two units have been combined into a single unit. So number of mechanical units or electromechanical units have been reduced, thereby increasing the efficiency. But we are still focusing on storing the hydrogen and oxygen gases. So when I say gases, again, the safety concerns are there. We moved ahead from here. What we did, excuse me, we proposed a new modified URFC. We have termed it as a proton battery. Why? Now you see the difference. I'll take you to the back slide. Here you can see the cylinders, the compressors, but in the next slide, the cylinders and the compressors are obsolete from the picture. Why? We are not producing any oxygen and any hydrogen gas, and we are not storing the hydrogen in a gaseous form. We are storing the hydrogen as a chemical compound. This is called electrochemical hydrogen storage. How it is being done? If you see the black strip in a unit, which is referred to as hydrogen storage electrode, it's a porous carbon-based electrode which has got the range of micro and ultra micro pores which can arrest the hydrogen in ionic form as a physical adsorption under the influence of van der Waals forces. Also, it has got the macropores, which are the pores of slightly larger diameter, inside which the hydrogen ions go in and they form chemical compound with the host material. This is how the hydrogen is being arrested in a chemical form or electrochemical form in the electrode, which is made up of porous carbon or activated carbon. The rest of the operation remains the same. The single unit acts as electrolyzer when the hydrogen is being produced by splitting the water, but instead of allowing the hydrogen ions to produce H2, the single H is arrested in the storage material, which is made up of carbon generally. Why carbon? I tell you how. Now, this comes up from a beautiful concept of multi-level car parking. We have termed it as carbon H park concept. Now, refer these in the multi-story car parking. These cars are referred to as H, which is hydrogen, and the spaces which are meant for car storage, they are referred to as a porous carbon medium. Now imagine this multi-story car parking where the hydrogen cars are coming in, getting stored, and when they are required, they moves out of the car parking and deliver the electricity. They produce the electricity. Why we are interested in carbon for H storage? Because carbon is a poor catalyst for H2 production. We do not want a hydrogen gas. We do not want H and H molecules to join together to form H2. Okay, it's available in abundant carbon. It's lightweight. I mean, the atomic mass is 12 when you compare it with, say, nickel or cobalt or other, which are used in the complex metal hydrides, which are commercially available, AB5 or AB2. The carbon is far more lighter than these material. Then the carbon, it's a porous media with very high surface area, and more the porosity, more the internal surface area, it's more better or more storing sites or storage sites are available for the hydrogen. It's very inexpensive, at least for the precursor. Now have a look on this image. As I said, it's a porous medium. It has got all sort of pore or pore size diameters from macropores to ultra micropores. Now diameters of the pores which are greater than 50 nanometers are referred to as macropores. From 2 to 50, these are mesopores. 0.7 to 2 nanometer micropores, and less than 0.7 meters are referred to as ultra micropores. Ultra micropores are the particular pores which are responsible for arresting the hydrogen hydrogen molecules under the influence of van der Waals forces. Now, if you see, the smallest diameter pores are shown on the right side. They are marked as ultramicropores, right? And rest, all these pores, they play a significant role in transportation of the hydrogen molecules inside these deepest pores. At the micropores, these inside surfaces, these are available for hydrogen molecules to form a chemical bond with the host material. Okay, and these chemical bonds are not very strong. When we start extracting or drawing out the current, under the potential difference which is created, these bonds break, and the stored hydrogen, they move out of the storage, and then they are ready to react with the oxygen to give you the electricity as well as the water. This is how this is the exploded view of the proton battery or the modified URFC that we have made on the research desk. It is a sandwich of various materials. There is a GDLs, gas diffusion layers. This is made up of titanium. Then this side is again GDL made up of carbon cloth. Then we have the MEA. MEA is membrane electrode assembly. This is the heart of the cell. It's called the polymer membrane. This is mainly responsible for exchanging the protons of hydrogen which is being produced from anode side to cathode side, from one side of the cell to the other side of the cell. Consider it as the middle portion of the cell. It divides the cell into two halves. The left side is called anode and the right side is called cathode. Okay, and if you see this gray colored portion electrode, this is the carbon electrode soaked in sulfuric acid. Sulfuric acid is another liquid proton conductor. It helps in the transportation of hydrogen molecules inside the storage material. So it's a sandwich. It's bolted up, and then we use it for storing the hydrogen and using the electricity. Since the electricity or the charge is stored in the proton, the hydrogen protons are traveling from left to right and right to left. We have termed this entire cell as a proton battery because it can store energy in the form of hydrogen. This is the central portion which I'm talking about, the cell. It is the MEA. It is made up of a polymer membrane. The chemical name is perfluorosulfonic acid. It's acidic in nature. It has got the inherent property that it allows only protons to pass through it, but not the electrons. And the electrons, they travel through the electrical wires. It has got this catalyst loaded on it, okay, which is responsible for hydrogen splitting and water splitting. It's called hydrogen reduction reaction and oxygen reduction reaction. The actual view of the battery looks like this. These are the end plates. You can see this is made up of SS316 because of the acidic nature which is prevalent in the cell. The SS316 is quite stable in the corrosive environment. So you can see the flow channels, which are micro flow channels, which are machined in these end plates. These are the bipolar end plates. And then when we put up the GDLs, the MEAs, and remaining constituents in it, we bolt it. And the lower picture which you see on your screen, this is the assembled proton battery. That is the sandwich which is complete. This is connected to the electrical terminals to supply the current or to withdraw the current, to draw out the current. And of course, it produces, it consumes the water and it produces the water as a byproduct. So respecting the time, I'll wind up very quickly. So the future vision for energy storage is coal, but for storing energy rather than producing the energy from a burning coal. So we are still relying on carbon, but now as an energy carrier, not as the energy source for by burning it. So the takeaway from today's session, so you must know that there is a distinct difference between green technology and sustainable technology. Not all the green technologies are sustainable, as I mentioned already. Lithium batteries, they cannot meet the global energy demand, and lithium is very, very costly to recycle. It's toxic in nature, and it emits fumes. Batteries that do emit toxic fumes and are self-discharging, and recycling, again, I said, it incurs huge cost. So efforts must be made towards making the surroundings. All must try to contribute towards development of a sustainable society. I'm happy to take up the queries. I could be reached on the email, which is highlighted in yellow color. And thanks for being the patient listeners, guys. Thank you. That would be all from my end.
Thank you, sir, for sharing interesting facts. I must say it would have helped students to gain deeper knowledge and would have helped future innovators to understand how important it is to invent a sustainable green solution. Now, I would like to invite Dr. P.S. Vijayakumar, scientist, Institute of Nanoscience and Technology, Mohali. He is known for his work in smart food packaging materials. Dr. Kumar, after completing his graduation from Tamil Nadu Agriculture University, took different postdoc experience from renowned labs. He also worked with Professor Ye, whose lab has been among top 10 labs by Thomson and Reuters citation in ranking. He has also been trained in nanotoxicology and biocompatible materials during his 6 months at NIOSH in US. Dr. Kumar has high impact publications, patents, and has been awarded as Outshining Reviewer Award in Elsevier, as well as has been finalist in Swiss Young Researchers. Sir, I invite you to present your views on smart material designing for future agriculture. Please, sir.
Is the screen visible? Sorry.
Yes.
The PPT is visible, right? Hello.
Yes, sir, it's visible.
Yeah, right. Thank you. Yeah, thank you for the nice introduction. So before going to the talk, let me thank the organizers, the PSCST, especially Dr. Bath, for organizing this event, VIGYAN UTSAV Punjab Future Technologies. Here I am going to deliver a talk on smart material designing for future agriculture. Already we are running out of time. We are 5 minutes beyond the time for this event. So I'll try to wind up by 10 to 15 minutes. So will that be okay?
Yes, sir. Please,
Yeah.
sir.
Yeah. So this is the outline of the talk. Very briefly, our institute, an introduction about nanotechnology, as because this conference is not on nanotechnology. I'm the first person going to present the smart material that we are designing for the agriculture through nanotechnology. I'll give a brief outline. And then smart fertilizer, and of course, as in the introduction, they have said a smart packing material that we have developed, and then a quick conclusion and acknowledgement. Okay, so this is our institute. So it is located in Sector 81. This is very new institute. I mean, 7 years before it was established. However, we moved to this building just a year back. Okay, last year we entered. Whomever crosses through the institute can have a look and try to get in and interact with us. You're always welcome. This is just next to ISER campus. Here we explore three diverse areas, that is chemistry, physics, and biology. And either we explore the material by itself, or the material will be created for some application. So in that case, in chemistry, it is catalysis, novel structure energy, and in case of biology, it is chemical biology. Cancer therapeutics is a big group, and I myself working on nano for agriculture. And in case of physics, strategic material computation and nanostructured devices, they concentrate on. So what nanoscience is? So just try to see this area. Okay. So a particle that is made to confine in all the X, Y, Z direction in the nano size is called nanoparticle. Okay. When such particles are being made, that gives a new property that has not been observed before in the bulk size. Okay. For you to know about this, I will spend next slide on this. Okay. Apart from this, if the confinement is in X and Y direction, and the other direction, if it is growing, it is called nanotube or nanowire. And if it is confined in only one direction, in other two direction, if it is growing in the bulk scale, it is called nanosheet. Okay. So based on these dimension confinement, it have a special property in either in optics or in magnetic or in electric, mechanical, physical, and chemical. Okay. Say for example, magnetic nanoparticles, although it become magnetic, only when it is exposed to magnet, it behaves the magnetic way. And when the magnet is removed, say for example, this magnet is removed, and again it goes to non-magnetic colloidal material, that is called super paramagnetic material. How it is useful? You can concentrate it in the body wherever you want by putting a magnet, and then you remove it, it becomes colloidal and it moves in the blood. Okay, that is the application that it gives because of the super paramagnetic property that is being explored with the nano confinement. Okay, this is the optical property. When the particle is confined to XYZ to a nano regime, okay, say for example 13 nanometer, it gives this kind of wine red color, unlike the bulk gold that is in yellow color. Okay, this is because of surface plasmon resonance. Because there is not much time, let me not explain this much, but the application is, because it is size is reduced, it can freely float in the blood. Okay, and it get concentrated in some region by using antibody antigen, okay, interaction, or with some tagging molecule like folic acid that is able to locate these material to highly growing cells. Okay, and then because it is in this color, it have an absorbance at 520 nanometers. So if you use that 520 nanometer in a mild strength, it will not scorch your skin, but it will penetrate inside and it will be converted to thermal. Photothermal conversion happens. The optical material helps in the light to get converted to thermal. Okay. So when you have a thermoresponsive polymer around it, that will denature and give out the drug. So you give a targeted drug therapy. Okay, here what we have done is, okay, we have made a particle in a nano rod kind of thing. Okay, this gives an absorbance at 850 nanometer, and you make a nano rod in another shell. Okay, here plasmon hybridization happens that shift the plasmon to 1000 nanometer when compared to here. Initially, I said the particle will be having 520 nanometers. When it is a rod, it goes to 850. And when it is a rod in shell, it goes to 1000 nanometers. Okay, this is a material that we have did. And because NIR can penetrate further deep into the cells, you can give a targeted therapy in a more precise way. Okay, now coming to what am I doing in our lab? That is, we are focusing on agriculture nanotechnology. Okay, that is in production, protection, preservation, processing. Okay, we try to design material for each of these applications. Okay, coming to production. Okay, we have made a smart material that can give the nutrient to the plant only with the when the plant needs it. Otherwise, it stays stable. Okay. And in case of protection, we have developed several methods that can deliver the pesticide in a targeted fashion, that can deliver the fungicide in a targeted fashion, that can give the pheromone and give insect control in a targeted fashion. Okay. And in case of preservation, we have made a nanoparticle based wrapper like this. Okay, that is loaded with heavy amount of preservative, and it can give the preservative in a targeted fashion to the fruit and protect the fruit from early ripening. Okay, and then in case of processing, we have developed a nano disc with the upconversion nanomaterial, which can convert NIR light into UV radiation. Okay, so this UV radiation helps in the conversion of ergosterol in the mushroom to vitamin D. Okay. So further in all these areas, we are also trying to explore sensing part. In case of sensing, we are developing optical based sensors and chemoresistive based sensor and electrochemical based sensors. Sorry. Okay, coming to the fertilizer. Okay. Fertilizer, there are two problems. One is leaching problem and the other one is unavailability problem. Okay, if it is a mobile nutrient, it will be leached out, and if it is a non-mobile nutrient, it will be becoming unavailable. Okay. So here we have taken iron fertilizer, which is non-mobile. Okay, it gets immediately fixed in the soil as iron oxyhydroxy forms. Okay, so here we have developed this kind of cage, mesoporous cage, which is loaded with iron, which is noted in a green color. Okay, and then that is coated with a polymer. Okay, this polymer have the ability to control the carbonate ions in the soil to enter inside. Okay, it serves as a gate. Okay, so the carbonate ion cannot enter inside, and hence the iron is available as iron form. Otherwise, it gets to convert to oxyhydroxy forms. Okay, but when the root comes nearby, since because it is able to exude out proton ions. Okay, this is just 2-3 mm around the root. Okay, root cylinder. Okay, so these protons open up the polymer and help in the taking the iron. Okay, that is how we have made a targeted fertilizer delivery system. This is patented. Let me go to the next one. Okay, so this is a kind of mesoporous material that we have developed in a lab scale way. Okay, where we have to use a template on which the silica is coated. Silica is nothing but sand, you can say. Okay, so this is very compatible to use in the broadcasting. Okay, so what we have done in place of the conventional template, that CTAP surfactant, which is expensive, that is being used in the lab, here we have used jute fiber. Okay, the jute fiber has been coated by the silica like this. Okay, and then it is loaded with urea. Okay, and then you are able to give a controlled release of the urea. Okay, as such, if you are using the fiber, one is the fiber will immediately get degraded. Okay, so the silica coating helps in the reusability. Okay, and the next one is it also gives a skeleton like structure that if you press the sponge, okay, every time it retains to come back to the same position. So it can n number of reusability. Okay, every time you can load the fertilizer and then you can deposit on this sponge can be deposited on the plant. This we have shown that after silica coating also the nutrient loading capacity is as good as naked fiber. Okay, with the confocal microscope. Now coming to the smart packing system. So for smart packing system, we have used a carbon sheet. Okay, the carbon sheet is basically the graphite. After getting exfoliation, you get the carbon sheet. Okay, so what is the property of this carbon sheet? Okay, so it can bind to anything that comes inside. Okay, that's why carbon filter is being used in the water filter. Carbon filter is being used in the chimney. Okay, so here we are using this carbon, the same carbon graphitic sheet, which is energetically favorable, high energy on the surface. Whichever comes on the way will be absorbed. Okay, so the preservative that is being added, this blue diamond like, hexagonal like shape that is added, immediately binds to it, and it shows a 200% loading on the carbon. Okay, so this is casted into a wrapper. Okay, by using simple vacuum filtration. Okay, this wrapper is being used to fold the banana, and since because there is 200% loading of the preservative. Okay, whenever there is a over ripening happening, okay, it releases the preservative and protects the plant from early ripening. Okay, why this is being done is because unlike otherwise, what the present way of doing is exposing it to sulfide gas. Okay, that sulfide gas converts the fruit phenol into sulfidic phenol. Okay, which avoids it converting to lignin by the lignin oxidase enzyme that is being produced by the over ripening of the fruit. Okay, that is why the fruit becomes black when it is over ripened. Okay, so this way of protection, that is using sulfide gas, okay, that is converting the phenol into sulfide forms. Okay, that is basically carcinogenic. That shows in a chronic effect. Okay, otherwise also those eco-friendly preservative, whatever the people say, okay, parabens and what is that, imidazine, okay, these are also having known to have chronic effect. So now we are the same parabens we are immobilizing on the carbon, and that is being cast into a wrapper, and so this parabens is not directly in the fruits, so you are having the health effect also by using this wrapper. Okay, so this is about the preservative that is used for smart agriculture. However, considering the time, let me go directly to thank you all. Okay, so this is the conclusion. Thus, we have developed a smart fertilizer, okay, smart pheromone system, smart preservative wrapper for the preservation of the fruits, and then a processing technology to enhance ergosterol, that is vitamin D. Okay, we do outreach, and I wish to thank my funding agencies, SEB, ICA, and DST, DRDO. Without their support, we will not be able to do this work. And I thank you all for being interested in our work. Thank you.
Thank you, sir, for deep insight to the technology. As we approach to closing ceremony of Vigyan Utsav today, allow me to pay my gratitude to all the eminent speakers for a power-packed, knowledge-driven session. I'm thankful to Department of Science and Technology, Government of India, for holistic support for organizing Vigyan Utsav series. I'm also thankful to all the students, researchers, faculty members, and scientists who have joined us today. My thanks are due to all my superiors, team, and colleagues, supporting staff for their earnest efforts to make this event successful. Thank you all.